Good evening. As you know, Professor Shechtman got his Nobel Prize for the work done on a micro scale, quasicrystals, while Professor Smoot got his Nobel Prize for the work done on macro scale, galaxies and supergalaxies. What these two worlds have in common and where they differ from each other. This is the subject of our conversation tonight. It starts with two pictures. On your right side, you have a picture from a microworld, quasicrystals, while on the left side, you have a picture from a macroworld, galaxies and supergalaxies. Do you see the similarities and differences? Let's start our conversation. Any question you have of any nature, it's informal, and you are free to do any question you want. Please, Professor Shechtman and Professor Smoot on stage.
And there's a little less underlying the laws of physics are very much the same, but this ends up looking more structured because it's a more confined system.
All laws of physics are applicable, or most of them? All laws of physics are applicable, or most of them in both cases? Same, all of them. Okay. Very good. Yeah. So we have this also. It looks like galaxies, structured galaxy, no? The one there, structured galaxy.
No, that's clearly a crystal. We know because it comes up on that side.
Oh, okay. Oh, okay.
You didn't order it carefully.
Yeah.
Where does micro ends and where does micro starts? They meet somewhere.
Yeah.
Right? So let's say that the Earth is the limit between.
No, it's easier to calculate. You take the largest distance in the universe, which is the horizon that we see, is the horizon size, and the smallest object that we know, and the geometric mean is the same size as a human. It's on the scale of a human being. So that's the dividing line between macro and micro.
It is clear that the scale of our system, the sun and the earth, and is affecting us. We get the energy from the sun, so it affects us. Is this the limit of the effect on on the earth? Is the sun the limit? And beyond that, almost no effect.
So the answer to that is in basically we know that the sun and the moon have by far the greatest effects on human beings. There are other very small effects, right? So it's a question of degree, how much going on. But in terms of our daily life, the sun is dominant, the moon is subdominant, creates the tides, it creates many other biological rhythms inside of us. Those two things dominate us. Where the planets are, it's very small effect compared to those.
I'd like to say a few words about the microworld, which affects our life tremendously. You see, let's take one subject, the human health. People died from diseases by the millions in the past because we did not know that there are bacteria. And when Leeuwenhoek developed the first microscope, Leeuwenhoek was the man who knew how to polish lenses. So he made the first useful, there were microscopes before him, but not as good. He made the first microscope he was a cloth merchant. He was dealing with fabrics, and he wanted to see the quality of the fabric. So he developed a microscope to look at the quality of the fabric. And then, in one of his, and he was a very curious person, and he looked at a drop of water that he took from outside, water that was sitting there for a while. And he saw little creatures there, which he announced. And then he developed his instrument further to see the first bacteria. And only then, people realized that bacteria can cause diseases, and this is how modern medicine started. First, with the development of the first antibiotic, the sulfa drug. I wonder only the older, the doyens of the people here know about sulfa. I received sulfa when I was a boy for a disease. This is an artificial, chemical antibiotics. And then the discovery of what we call now the penicillin and the antibiotics that come from nature. So it was the microscope that enabled us to be here, because our forefathers did not die, because they learned how to control diseases by developing medicine. This is just how the microworld can help us. Where does microworld end? What is the smallest that we can see? In electron microscopes today, you see atoms. I showed you one picture, but you see much better pictures today. This is where the limit is, the limit of resolution. The resolution of our eye is about 1/10 of a millimeter. This is 100 microns. You cannot see more than that, closer things. But the resolution of an electron microscope is 1 angstrom. This is 10 to the 7th better than our eye. So we see 1 angstrom, which is 1/10 of a nanometer, and our eyes can see 100 microns. So the small world affects us tremendously. All the communication system, transistors, all this is the microworld. It affects our life, it affects our health, it affects us everywhere. And if you go to the macro, from here, from atoms and smaller particles, elementary particles, we can go up to the solar system. And this is our world. Beyond that, it's nice to know, but not really affecting our life.
What's the penicillin of the galaxy?
I see. No, let me agree in a certain sense and disagree in another sense, and that the macro world does not affect us so much right now, because what it did was create the situation where we live in. If the macro world didn't exist, we wouldn't have the elements, we wouldn't have stable solar systems, we wouldn't have the situation where the stars, like the sun, can burn for billions of years and provide a stable environment which we can hope to maintain for some time. So the existence of life owes itself to the fact that first space-time was made, then the elements were made, and then the stars, and the next generation of things came out of that. All that ended up, through this long series of processes, taking fundamental building blocks, building up a much more complex system, allowing for there to be chemistry and allowing for there to be life. So in that sense, it affected us profoundly, but it doesn't affect us actively and threaten us actively the way we do now, unless, of course, a gamma ray burst should go on the galaxy and its beam should go through us and we'd be vaporized.
Right.
And so there are external threats, but we generally ignore those because we're in any position to deal with them now.
Okay, so the macro world prepared everything so that we can be here, and from now on is the micro world, unless a disaster occurs.
Right. An
Something
asteroid
comes from
could-
heaven
yeah.
and says, goodbye, Earth.
When we were in Chongqing, we were discussing about can human race can go another planet or another galaxy. So you did a special calculation. Can you tell us? This was very interesting. Apparently, we are in a difficult position as a planet in the future, according to George. What was the calculation about?
Right. So one of the questions that was asked to me was, can we find another planet that's habitable? Because one of the big news that's going on in the field today is that we're discovering planets around other stars on a very regular basis. And we're guessing now that at least 10% of those stars in a galaxy have planets around them, and maybe half of those have a planet that's in the zone we think is habitable. So people are saying, if we should destroy the environment here, can't we flee to this other habitable planet? And the answer is, it would cost the whole energy output of the Earth for millions of years to take one small colony to one of these other planets, and it's a highly risky journey. I mean, as I gave an example, the nearest star systems, that means if you travel at a reasonable speed, which you can do with chemical rockets or nuclear propulsion or something like that, it's going to take you thousands of years to get there, and you have to provide resources to support life. And I said the only sort of way I can see is generally you will send machines, but if you really think it's very important to send humans, you'll send frozen fertilized eggs, and there'll be robotic nurseries that will raise the children. But the people who are alive now on this planet, they're stuck with this planet. They're never going to be on another planet except in our own solar system.
Except only if there are some new laws of physics.
Right. The only way we could get around it is if we could discover some new laws of physics, even though we believe that those are still going to be very expensive energy-wise. But if you're really desperate, you build an ark, right?
So any other question from the audience? Any, not just science, but any curiosity you want to know? Doesn't repeat the issue to have two Nobel Prize in a dinner like this, so you can grill them in a good sense of the term.
Grill them for dinner?
Let me suggest something. Sure. Let me add one more. There is a question there. Is there? Okay. Yes.
I have a rather fundamental question to colleagues here. There are not a lot of students around. There, as somebody mentioned today, there are a lot of professors. And I would like to express my worry that as a physicist, what I notice in my own career, that moving from metallurgy, real metallurgy, material science metallurgy, to perovskites, and now I have to really engage organic chemists to really help us to solve the, say, electrons from vanadium redox batteries. So what's worrying me on there, as a physicist, we are not trained to be a chemist. If I want to be a chemist, I'll study chemistry. If I want to do chemistry, organic chemistry, I'll go to organic chemistry. Somebody today during the talk mentioned there's a dramatic difference between organic chemistry and inorganic chemistry, and the work which he presented would be impossible without help of organic chemists. What worries me now on shoulders of physicists is enormous pressure now to be expert in everything, especially with organic materials. I fully appreciate the work and sheer, actually, science coming from this, what we had today, but I would like to just mention this, which is my major worry, that we probably should really look at the education of younger generation when the physics and organic chemistry curriculum must merge together. Otherwise, we are losing physicists. They will go to quantum, some modeling, but not really dealing with the mixing and preparing missiles and monomers. They are not familiar with this. They are not trained. So what I'm worried about this, it looks like when I attended MRS conference December, I was shocked because last time when I was in MRS was a lovely environment, lovely, beautiful cross-section. This time MRS was absolutely everything about the organic chemistry. So I would very much appreciate the comments. How do you see, maybe modification of physics courses, or looking at the physics and organic chemistry together, not inorganic chemistry, organic chemistry. What is your view?
So basically, organic chemistry and physics,
Right.
how
All
they
right.
can get together.
How they're linked together?
Yeah. I can make a
Similarities
comment
and
while he's
differences.
gathering.
Well, let me
this.
tell you something. Look around you and discover what is not made of plastic. So you realize that the glasses are not made of plastic, and maybe a few more things. Everything else in this room that you can see is made of plastic. The floor, this, everything, almost everything you wear, the ceiling, the paint, polymers, plastic. So the discovery of plastic, I'm trying to answer a question, changed our lives. It enabled us to have wonderful materials which are all over us, including what we wear. I wear cotton, but most people don't. And the underlying is the laws of physics. The laws of physics control all of this. And they determine what can be done and what cannot be done. The laws of thermodynamics controls and tells us what can be done and what cannot be done. And there is no perpetuum mobile. We know that. And many other things which I will not dwell on right now. It's not a real scientific meeting. So what should we expect? What should we expect? Are we going to discover new materials? Yes. Are they going to be useful? Yes. Where is the breakthrough? Nobody knows, but it will come. What is the field that is going to develop most? In my opinion, medicine. We are going to conquer the major diseases of today, which is cancer. The diseases of cancer, the different cancers, we are going to conquer that in many of your lifetimes. So this is the current disease that we don't know the solution, but we are getting there. We are getting there, step by step. We understand better and better. And there are breakthroughs being done every day now. We understand it better. We're going to solve that problem. Before, it was influenza that killed people, or germs that kill people, viruses and germs. Now, people don't die of that usually. Now it's the other diseases, heart disease and cancer. Heart disease, we solve by mechanical means and other means. It's getting better and better. Cancer, we're going to solve in your lifetime, in our lifetime even.
George?
Okay, so I have a couple different things to say about that. And I want to draw a distinction between the knowledge and the techniques of organic chemistry, which are a powerful part of the scientific legacy, and the idea that organic chemistry is separate from inorganic chemistry or physics. That's a sort of an old style definition. There is, during the days when people believed that things that were alive had other things in them than simple chemicals. Now I think no one will be surprised when someone completely creates a synthetic life form and it has all the properties. There's a lot of issues involved, but that's something that we're well on the way to doing, may have already been done. And so the thing that you can look at and see is the fields have become more integrated. When I was first being a professor, the third year quantum mechanics course was a course for physics majors with just a few other people. Now it's a service course for us. That is, when we teach the third year quantum mechanics, most of the students are not physics majors. They're biologists, they're chemists, they're computer scientists, right? Because those fields are becoming integrated, and now we do biophysics and we do quantum mechanical treatment of systems, and we actually study the mathematics of large complicated molecules, and we also do experiments to measure the tension. You know, the folding of a protein, what force does it take? How much energy is stored in that? What's the gain? Those experiments are being done by new tools that are being created because physicists are getting in that area. And so the idea of biology and organic chemistry and so forth, that's being very blurred. And it's natural, and it's true. What we really need are more scientists and more engineers, right? Because in fact, as it gets blurred, you need people with deeper, more fundamental understanding to do the basic science, and people with better training to do the engineering, because the level of engineering is increasing quite substantially. Because we are going to be making synthetic life forms. We're going to be making modified life forms.
Google has a project to extend the life of human being, actually to eliminate death. I don't know the details, but you mentioned that you can increase life in a certain way. You just, in Chongqing, you mentioned this during breakfast with
Yes,
me,
we were
but
talking
also
about
you
here.
mentioned at the
Yeah.
table here.
Okay, I'd like to add something.
Yeah.
You know, technology of today is based on science. Before microscopy, people knew how to make good steel, but only by experience that was transferred from father to son to grandson and so on. The knowledge was practical, but they did not understand what they were doing. With the start of microscopy, we started to understand what we are doing. I can tell you that the Wright brothers, who flew the first airplane, they built an engine made of aluminum. Probably the first engine made of aluminum was for their first airplane. They did not know what they were doing. They did not understand. Now we understand that they did a marvelous job. They created modern aluminum alloys.
Yeah.
Now we know, people at NBS where I work studied a part of their engine, and they say it's marvelous, but they did not understand. And now you go to the store and buy aluminum foil for a couple of dollars and look at it. It's fantastic. Let me tell you something. On the top of the Washington Monument in Washington, D.C., there is a piece of aluminum. It was more expensive at the time than gold. To make that piece, it was a major achievement. And look at where we are now. Airplanes are made of aluminum. Aluminum foil for the kitchen. Tremendous product. Look how perfect it is. You roll it, it looks normal that you have it. Do you know how difficult it is to make it? It's amazing. It's an amazing achievement. And we can do that because we understand the microstructure of these materials. Microscopy again. When we cross the border between the resolution of our eyes to see smaller things by microscopy, we entered into the world of modern technology. This was it. We saw in our own eyes the microworld. That was a major, major achievement.
Yeah.
So I mean, I'll add to that we're entering the age where we're beginning to learn how to manipulate things at the atomic level, that we can build things by atoms or by molecules, whereas before we could just do bulk material. So most things we still do now using bulk material, we do amazing jobs at it, but the time is coming when we're actually going to do it atom by atom. There are devices that we work on in the lab where we put down 3 layers of a certain kind of atom, 2 layers of another kind of atom, 3 more layers in order to make a series of tunnel junctions. That's the beginning of actually making molecular machinery.
Mm-hmm. Mm-hmm. How difficult to change the subject? How difficult it was for you to go against all people that were not in agreement with your discovery? This is a very interesting point. People want to know. How you mentioned a dog there. What?
Okay.
What do you suggest if someone else here is in the same position?
Okay, this is usually a question good for students. How to overcome fear of authority in science and fight against authority in science. Well, I mentioned it in my talk. In order to protect your findings, you have to make sure that you're right. And you can make sure that you're right if you're a professional in a certain subject. And you are very good at it. Once you are very good at it, you say, okay, I tested myself several times, and I trust my findings. If you want to contradict what I'm saying, repeat my experiment or repeat my calculation if it's about a theory, and show me what is wrong in what I did. Telling somebody it's impossible because it's not in the book is not good enough. Telling somebody it's not possible because of thermodynamics, that is a good argument. Show me why it is not good, why it is impossible because it's against the second law of thermodynamics or something like that. That's good. But I was sure that I was right. And I can tell you that the first fight that I have to fight was in the closed environments of the laboratory and adjacent laboratories. I didn't have to face the world. When the publication came up in 1984, at the end of the year, shortly thereafter, I was not alone anymore. I had many people repeating my experiment and declaring, he's right, and we are together to protect this vision. So we were a growing community, an avant-garde community of young scientists who knew that everything is correct. And we had to fight the old generation of people who believed in what is written in the book. But this is typical to every profession. Old doctors, physicians, do not adopt new medicines usually. It's the young physicians that adopt the new medicines first. They can take the risk. Oh well.
George, just you had some resistance also, but not at that degree. People were skeptical of your discovery also.
I think that was true, and I think along the way there were many big hurdles to overcome, including wanting to go to space in order to do it and having the shuttle blow up. So I never knew anyone who didn't face difficulties and hurdles anytime they started on a major project. It seemed to me that I faced a lot, but I wasn't going to let anyone stop it because we knew that if it was the only way to find it out and see what the world was like.
Well, just another thing I was thinking. You recognize this, yes? It's long ago. What about this one?
Yeah, I recognize it. You don't have to laugh.
So you're young. Now you're Nobel Prize, but not at that age. What's the difference? What's the best position to be in?
It's hard to say, because when you're young, you're full of promise, and when you're old, you're full of accomplishments or not. Right?
So just to conclude, because we have a very good show coming, I think there is no other question, but just to return, you mentioned how you extend the life, just short.
What?
And then how you can extend life, you were mentioning.
I see. Well, it's a different logic, but
Yeah,
okay. So we're having a little discussion here at dinner, which is similar to ones I've had before, and that is, I often ask my students this practice exam question: when will human life expectancy become infinite? And the students always answer, no, it will never become infinite. There's too many limitations. People have flaws and they're going to fail, right? They used to say that we had diseases and you wouldn't be able to cure them. And then we had degenerative diseases and you won't be able to cure them, although you heard Danny say that. And I give them a hint. I say, during the last century, every 10 years you lived, you gained 1 year of life. And that was all due to basically civil engineering, improvements in sanitation, improvements in refrigeration, improvements in food delivery, and growing and so forth. But during the last part of the century, and there was a little bit in medicine, namely, immunization against certain bacteria and so forth. But towards the end of the last century and the beginning of this century, there's been real advances in medicine, and life expectancy is increasing by more than 2 years per 10, and it's increasing. You can expect in the next decade you may gain as many as 4 years for 10 years you live. And so how long will it be before it's 8 years for 10 years of living and then 16 years, right? Just do the calculation. And the students do the calculation, and they find it's somewhere between 20 and 40 years that people will be gaining more years. For every year they live, they'll get more than one more year of life expectancy. And the students all object to that, because it's a lot of problems. But one of the things is, if you're one of the people who is dumping waste in the ground, figuring it won't be a problem, or you're polluting the air or something like that, you're going to live 1,000 years. It does matter to you, right? So there's a lot of assumptions built into people's behaviors, how long they're married, how long, what they do with their lives is based upon they were expecting to live to be 70 and then die, right? And so now they have to recalculate in such a major way, it's too much for people to deal with. And so you can expect that you will live much longer. We've already seen a lot of evidence of that. Every pension system in the world is in trouble because people are living longer. That's good, people are living longer. It's bad because the system is based on people who will not live longer, right? And so you see all those kind of features. So the question of environmental sustainability becomes much more important to you when you realize you're going to live for a long time. If you live for 500 years, think of what the advances in medicine are going to be in 500 years. So how much longer you live than that? And can you afford to pay the medical bills so you can be rejuvenated, right? You have to start working harder and investing more. You can't retire early. So there's huge differences that you start thinking about, and it makes you rethink your position in the world, but also society's position in the world.
Quasicrystals and life. Can you use quasicrystals to extend the life?
How useful is it?
Quasicrystals, quasi-periodic crystals, and the life. Can you use it?
Are you asking about applications?
To extend the life.
Applications?
Yes.
Okay. Well, quasicrystalline materials have different properties than many other materials. And in order to find application, you look for a property which is interesting, which is different, which is better than other materials. So what are the properties that quasi-periodic materials have which are different than periodic materials? Well, they have many properties that are different. For instance, heat conductivity, low. Electrical conductivity, very interesting behavior as a function of temperature. Friction and wear, they are very interesting this way. Magnetic properties, optical properties, they have interesting properties. Based on that, there are applications. So what do we do with them? I'll give you one application that is useful in every kitchen. You can take a frying pan and coat it with quasi-periodic coating, and it is a non-stick coating, like Teflon, but it is metallic. You know, using a knife in a frying pan which is coated with Teflon is a bad idea, because you scratch the Teflon and it's poison. It's not advised. If you take a frying pan coated with quasi-periodic materials, it's not advised to use a knife because you will destroy the knife. So here's one. Catalysts to make alcohol use that. But let me give you something which is very modern. You know about 3D printers, three-dimensional printing of bodies. Quasi-periodic powders absorb the infrared readily. They heat up very quickly if you heat them with infrared light. They heat up very quickly. So if you take fine powders, fine quasicrystalline powder, and mix it with plastic powders and use it to build something, then you pass an infrared beam, very narrow infrared beam. Whenever it hits a quasi-periodic particle, that particle heats very quickly and melts the surrounding polymer around it, and it binds together. This is a technology. You can buy it today. And a company in France named Saint-Gobain, it's a huge company. They sell these products. They will sell you the powder and the machine and everything else. This is another application. There are many applications based on interesting properties of quasi-periodic materials. I don't get anything of this. I don't have any patent on quasi-periodic material.
Can you run for politics?
I don't think I want to run for politics.
Why?
I admire Danny being willing to do that, but that means he has more faith in the voters than I do.
And more guts. I forgot to mention during the plenary, probably some of you don't know, but Danny had the courage and the guts to face long time serving politicians in Israel. And he put himself up for president of Israel. It's not chosen by the people, but it's chosen by the parliament. So he did it. He had that courage. Unfortunately, he couldn't win this time. John Minch here
He got
tried.
1% of the vote.
So what's your impression about politicians that have spent all life in politics? I mean the real one. There is no politician here. There is no politician here, so just tell us the truth.
Our politicians, when I presented my candidacy, is that they say that I'm apolitical. They don't want to belong to any party. And I said that the president should not be a political figure. He should see the big picture, not just this side of the island. They deny it. Because they all see just one side of the picture.
Was it difficult to deal with them? You met all of them. What's the impression? Difficult in what direction? Just to have an idea, a glimpse. Not the secrets.
But let's talk about science.
Okay, good, okay. Well, no, I mean, it was just going
No, but
around.
I have to agree with that. My experience is most people, and particularly like in politics, so they have a very limited view of the world, and they're very much focused on eking out a small gain or a small advance, rather than thinking about what's the overall good, where are we going to, and that's the problem you face in sustainability, right? You need to get 200 countries together to agree on what's the right approach to fixing the world, and there's no way they're all going to have the same agenda. Right?
And why engineers and scientists are not able to get higher in political offices? What's missing?
I think most science and engineers are happy with a world that's rational and doesn't involve a tremendous amount of social interactions. And politicians, their whole world is about social interactions and about how to convince people to come around to their point of view and so forth. Whereas we're expecting that if we present the case very clearly and very logically, people will come to the conclusions themselves.
Yeah, but I guess that's the problem, because we cannot really, if we don't have rational in politics, I think that's what we are missing. No?
Yeah.
So what's the secret to break the glass?
Better voters. We have to educate the voters to vote for people who are doing a good job.
So this voters.
Yeah.
What about you? You recognize this picture?
Yeah.
We're explaining about quasi-periodic materials.
What you see here is the people at National Bureau of Standards in Washington, D.C. A couple of years after the discovery, when it was already published. And we took turns showing to the others what we do. So this is the picture in which I show. And then I sat down and somebody else got up and he showed us. So this is just...
That's the only one, it's the most popular one, I guess. What about this?
You are back to politics. These are the candidates.
Yeah, competitors in politics, not in science. Who won? Who won? And I think the first guy.
The one on the right.
The first one. Or the last one.
The one on the right.
The other on our right.
On the right of the
That
people
right.
that go.
Oh, in their right. Okay. Yes, sure. Okay. Yeah. So, no, by profession, lawyer.
I think he's a lawyer, yeah.
Good. So they are better. Okay, now open for the questions. Any question you like. I reserve the last for myself. I have to be short though because we have a very good show.
See, nobody wants to ask a question, they want to eat.
Any question? No, Shah. Yeah, here. We have one.
And the question is on the last slide which you showed, which was showing a beautiful flower with a thank you.
Yes.
I would like to know this. Anything to look beautiful, is it going to have a quasi-crystal periodicity? I'm referring more to that number, which is Fibonacci series, the 1.681, because this number is also used for optimizing many things. So is it that anything to look beautiful, they have to have quasi-crystal periodicity?
Yeah. Can you repeat it?
I didn't get it.
I think he was asking, in order for something to look beautiful, does it
Louder,
have,
please.
in order for something to look beautiful, does it have to have a quasi-periodic crystal in it?
You showed the last picture of
Is it
beautiful flower.
Yes.
So he's asking, in order to be beautiful, should it be quasi-crystal on the side or something?
No. No, that flower, by the way, is a wild flower that grows in Japan, and it has a threefold symmetry, rotational symmetry. And I just saw it in one of my trips in Japan in the wild, and so I thought that it's a nice picture to show.
Because why I was curious, because of that number, the Fibonacci series number 1.618, something like that, because that number also we use in optimizing many things. And we optimize when that's the optimum thing that we get using those numbers. We got golden search techniques and those kind of things.
Can you repeat again, guys? Because
I was just referring to because of the Fibonacci series which were showing. That Fibonacci series had some number, 1.61 something. But you were saying that is the ratio with which this periodicity changes.
Right, the Fibonacci series number, the golden mean.
the golden mean.
Golden mean,
number
yeah.
showed.
Okay, what is the question about the golden mean?
Golden mean because this number we use in optimizing many things.
Optimize.
Optimizing, when we want to optimize certain activities in our thing, that number we use. We got golden search techniques when we want to optimize some parameters or some process. There we use that number.
You know, people call it the golden mean because they found that it has some aesthetic value. So this ratio of 1.618, people claim it has aesthetic value.
So quasicrystals coming now to the metallurgy, yes? That's what you mean. You see, it's one world and one galaxy. And the last burning question to conclude it, it's your symposium dedicated to your life achievement. What's the meaning of life?
What is the meaning of life?
Short, just in 2 words.
No, that's a really interesting question if you're going to live for a really long time.
Because I have two
You're going to
pictures
get
there.
bored
I
and
have
you're
two
going to want to
pictures
know
there.
what the meaning of life is.
Yeah. This is how we looked like in our half-lives.
When we're rejuvenated, we'll look like that again.
So what it is?
What's the meaning of life? It's what people make out of it. It's what they do. It's how they define, it's how they live.
For them, it's quasicrystals. Thank you very much. So we have a very good show coming. It's a miniature of I was told, of Cirque du Soleil. So I hope you will enjoy it. Thank you again. And don't forget, so it's a symposium dedicated to you. My doctor is 95 years old and working every day.
Ah, good.
95 years old, working every day. I go in the morning there if I'm sick. He starts working at 6 o'clock in the morning.
Very
His
good.
private clinic. Thank you.